Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we will start the development of the equivalent circuit of the synchronous machine, 3-phase synchronous machine. Our philosophy is very similar to transformer. First we understand the physics of the machine, then once we have understood the physics, of course transformers physics was very straightforward. Synchronous machine and induction machine physics is a bit more involved. But once we understand the physics of the machine, we have derived the torque equations using energy co-energy principle, and why do we need a 3-phase machine, why single phase machine is not good enough, 2-phase machines is something as an intermediate that we did, and motivation for 3 phases historically we have already studied. So, once we have developed all that, then we need a simple equivalent circuit of the machine to handle our day to day requirements. Just like for example, it's a example from a different domain, but let us say nutrition. Now carbohydrates are needed, proteins are needed, minerals are needed, water is needed, fluids are needed, stomach requires acid to create digestion and breaking down of it, kidneys need to do filtration and many other kind of things. So it is a very complicated system of how what we eat, it is converted. There also energy conversion is taking of form. After all, at the end of the day, you are creating, your body has a temperature, a living person's temperature is there and it is maintained by the body. So the chemistry is there, and then the electrochemical or whatever reactions are causing the heat to be generated, and then there is this energy has to causes the blood to flow and oxygen to be taken in the lungs, and it's another energy conversion machine. At the end of the day, if you look at it, it is no different. Here we are talking from electrical to mechanical, mechanical to electrical. In our case, we are talking of plants that we eat and water that we take, that is being converted into energy form which is sustaining the life form. Now, I mean, doctors or probably others in the biology or human physiology or whatever, they understand these things very nicely. We do not understand it here, but at the end of the day, if you look at it, finally when you go to a nutritionist or whatever, you need a set of guidelines, right? Like for example, if you do exercise, you should you burn so much amount of calories. Now you should compensate it by equivalently by taking that much amount of calories, and then muscle repair requires protein. So therefore you should take so much amount of protein. But then if you take too much of protein, probably it will not be, kidney will not, it will overload kidney, or it will be just thrown out of your system. So it comes down to all this knowledge, the science and all that, finally you filter down to some simple set of guidelines, rules and so on, using which, without every time needing to go back to all the detailed physics of it and getting probably even confused with all that and so on and so forth, because it requires lot of concentration to get to that level where you wrote energy, co-energy equations and took derivatives and all that. You would like to have some simple shortcuts which are useful in the day to day life. So, equivalent circuits is just the similar kind of a thing. in the machine's domain. The machine is a complex piece of equipment and its functioning is also pretty intricate and so on and so forth. Lot of care has been taken care of in terms of creating distributed windings, exciting it by distributed currents in time, distributed winding in space, carrying distributed currents in time, and making sure that harmonic voltages are not there, etc., etc., it is balanced, etc., etc. Everything is well taken care of, but do I need to everything time run through all of this detail before I use it? No, please give me a simple equivalent circuit which is end to end terminal based model of the usage model, and I will just like to work from there and do my most of the calculations. So many generators are connected to the grid, so many motors are connected into the grid, and they are all working in the grid. Most of the time I as a end user do not need all of this. You give me equivalent circuit and I am happy with it. I can do lot of things with it. We will see in some of the examples also. So, that purpose, to that a purpose, for that reason, we are now today going to discuss the equivalent circuit of the synchronous machine. So, our again the notion is going to be based around a motor model which we have been discussing, and a lot of things that I do not know whether I have mentioned it or not, but lot of these things I have picked up from this book, Power Circuits and Electromechanics, from Professor M.A. Pai, his book. And of course, this book is again based upon many other books like Fitzgerald, Kingsley, and I mean lot of references around that. But my teaching has been, especially on the machine sides, transformer sides, has been quite a lot motivated from this book. I worked with Professor Pai. He was a professor at University of Illinois. He retired from University of Illinois at Urbana-Champaign, but up to around age of 50, he was a professor at IIT Kanpur, where he was a dean also. He is a PhD from Berkeley, I think. He worked here, then he went on a sabbatical to US and then stayed back at University of Illinois, Urbana-Champaign, where he taught a course also on power circuits. He is known for his energy functions methods research, and he wrote a book there which he kindly gifted one copy to me. I spent some time in 2001 with him as a Fulbright research scholar also, and he is no more now, but it is an excellent book that he has written. His book on computer aided power system analysis was also once upon a time very popular book. Tata McGraw-Hill had published that book. So, a prolific researcher with his heart committed to India, that was the kind of person Professor M.A. Pai was. And this is a wonderful book. So, let us come back to it. Let us come back to the equivalent circuit of the synchronous machine. So, what we need to do first of all to create the synchronous equivalent of the synchronous machine, let me add a page somewhere and let me do it afresh. So, what we will do is we will first write the flux linkage equation. We will write the flux linkage equation for the A phase of the stator winding, and that is given by the self inductance of the A phase times the current that it is carrying plus its mutual impedance with the B phase stator winding. So, therefore, MAB is a constant times IB, and we have derived these constants in the previous class, plus its mutual coupling with the C phase, which is again also a constant because A, B, C windings on the stator are fixed distributed but fixed, times if the angle between the rotor winding which is carrying the DC current and the A phase of the magnetic axis of the A phase, and this is say vertical line, this is the magnetic axis of the A phase, this is the magnetic axis of the rotor, theta is the angle between the two. Then if when they are aligned with the two axes are aligned with respect to each other, the mutual coupling is a maximum at its value MAR, and now it is MAR cos theta times the rotor current which it carries. So, this is the flux linkage that the rotor winding will create in the A phase of the stator winding, and similarly these are the these four terms together tell me what is the flux linkage which is associated with the A phase of the stator winding. Only one term is theta dependent, all other terms are not theta dependent. So, I can further write this as Ls IA plus, or rather these mutual couplings we had seen was minus of Ls by 2 IB, and MAC also is minus Ls by 2. Ls is the self inductance of the stator winding. All the three windings on the stator being identical, their self inductances are same. All mutual couplings between the different stator windings are all minus Ls by 2, that also we saw last time. It comes from the fact that cos 120 degrees is basically minus sin 30 degrees, which is minus 1 by 2. Minus of IC, minus of IC plus MAR cos theta IR. Now, let us add and subtract, subtract Ls by 2 IA. This will obviously not make any difference to the net equation that I have written, but then this will become 3 Ls by 2 IA, and minus Ls by 2 I can take common, then IA plus IB plus IC times plus MAR cos of theta I of R. But then for a balanced system, IA plus IB plus IC will be equal to 0. So, therefore, this lambda A will simplify to 3 Ls by 2 IA plus MAR cos of theta I of R. Now, IA is, I can write it as cos of omega s of t, and of course, then you know that IB is Im cos of omega s of t minus 2 pi by 3, and IC is Im cos of omega s of t plus 2 pi by 3, that you know. So, now if I substitute this IA here, and for theta I can substitute omega s t plus of gamma. Why? Because you remember frequency condition was omega m is equal to omega s minus omega r, because the rotor winding DC frequency current, DC frequency is a DC excitation. So, its frequency is 0. So, therefore, omega m is equal to omega s. So, actually we had written theta equal to omega m, which is the rotor speed of rotation of the rotor times t plus gamma, but that omega m for synchronous machine is same as omega s. So, theta becomes equal to omega s of t plus gamma. So, substituting this here in the lambda A equation, we get lambda as 3 by 2 Ls IA plus MAR cos of omega s of t plus gamma times of I of r. So, I can, because IR is a constant MAR. So, I will write it as capital IAR, and this I will write it as this I will write it as Ls Im cos of omega s of t. So, this is my equation for the lambda a, and so voltage which is developed at the terminals is going to be the rate of change of flux linkage lambda a, and in this lambda a all the B phase C phase couplings have also been accounted for. That is why it has got 3 by 2 Ls, otherwise it would have got only Ls, and this equation is only valid for balanced currents, balanced operation. Otherwise all the other individual phase currents will have to be handled. These kind of simplifications that we are using here, this to be summed to 0 and all that may not be applicable, may or may not be applicable, it depends. So, we now write this as cos of 3 minus of 3 by 2 LSIM, differential of cos of omega t is minus sine of omega of t. So, that is why that minus sign has come, minus of MAR IR, again minus sign has come because when I take differential of cos, that is minus of sine of omega s plus t plus gamma, and one mistake I made, that let me correct for that mistake. So, whenever I take this derivative, whenever I take this derivative here, this omega s also will come here, and same thing I have to do here also. So, let me correct for that also. So, this will be minus 3 by 2 omega s Ls minus 3 by 2 omega s Ls Im sine of omega s of t minus of omega s MAR IR sine of omega s t plus gamma, which I can further write it as 3 by 2 omega s Ls Im cos of omega s t plus pi by 2, because cos of theta plus pi by 2 is minus sin theta, and again the using the same principle, sine of omega s of t plus gamma, I am sorry, plus gamma pi of by 2, this should be cos. This should be this should be cos. So, what do I see for VA? It is, both of them are sum of two cosines. It is like a cos of omega t plus theta 1 plus b cos of omega t plus theta 2, but then this is going to be some c cos of omega t plus some theta 3. So, sinusoids when scaled and added still remain sinusoids with a different maybe with a different amplitude and maybe with some phase shifting. So, therefore, I can write this as some Vm cos of omega s of t plus of delta, gamma is already used. So, I will write this as delta. So, now my job is to find out what is this Vm and what is this delta, that is the next job that I have to do. So, I will do it using complex numbers, I will you and Euler's identity. First thing what I will do is, I am going to call this 3 by 2 omega s Ls as something called the synchronous machine, a synchronous reactance of the machine, and I am going to write it as okay. So, I will call this as the synchronous reactance of the machine XS, and we are only looking at cylindrical rotor 3 phase machine, a synchronous machine. If the rotor is salient pole, I mean two pole machine, cylindrical rotor, two pole 3-phase synchronous machine, that is what we are studying. If the rotor is salient pole and having 4 poles, 6 poles, 8 poles, then the equivalent circuit is a bit more messy, we will not get into that, but the ideas will be similar but at the next level. So, I will get this as XSIM, and it is okay to call this as synchronous reactance because omega times L is reactance, right. So, there is only this scaling factor of 3/2, but otherwise it is basically a term of reactance. Omega L means reactance. The 3/2 is coming because the mutual coupling of the other two windings B phase and C phase also have been adjusted here. And I will write this as, for cosine, I am going to write cosine as real part of e to the power j omega s t plus pi by 2. Okay. So, this you agree, cos of omega s t plus pi by 2 is real part of e to the power j omega s t plus pi by 2, and because excess the synchronous reactance and I m, these are just positive scalars. So, therefore, I can keep them inside of the real part. So, this is what I will get, and similarly this I will write it as real part of MAR IR e to the power j omega s of t plus gamma plus of pi by 2, and the left hand side I can write it as real part of, so you can see this j to the power e to the power j omega s t is coming because I am trying to convert these sinusoids into phasor equations, and I am doing it all detailed here, but actually I can directly jump to that state also, but it is not such a great idea. We should do it properly, that is what I feel. So, I am writing it here as e to the power j omega s of t plus of delta. So, now I have got this. Now, what I will do is, let us divide this equation by root 2 everywhere. Okay. So, I will divide all these terms, let us divide all these terms by root 2 everywhere, because then I want to write things in terms of phasors, that is the basic idea. And then I will call Vm by, then I will call Vm by root 2 e to the power j delta as the phasor or a complex number Va, and here e to the power, this is e to the power j omega s t plus pi by 2, this can be written as product of two terms e to the power j omega s of t into e to the power j pi by 2, but e to the power j pi by 2 is nothing but the imaginary axis j under root of minus 1. So, therefore, I can write, what I can do is, I can write this equation as V A e to the power j omega s of t, left hand side, is same as this thing times, I am writing for A phase. So, therefore, j I have taken out common, not common, for j indicates e to the power j pi by 2 times xs I m by root 2, that is giving me the phasor current, which is reference, because I have taken it as I m cos of omega s of t. So, therefore, it is my reference reference current, its angle is 0. So, therefore, I m by root 2 can be replaced as I A and then e to the power j omega s of t plus real part of m a r I r by root 2, this I will just write as it is, into e to the power j. Okay. So, let us let me do this also first outside the third term. So, let me write m a r I r by root 2 e to the power j gamma plus pi by 2 as another complex number which also indicates a phasor called as E t. E t is the or I will just use E, I will just use E, the open circuit voltage seen at the terminals. So, okay, it is also fine, open circuit voltage seen at the terminals. So, we will connect it to why it is called as open circuit voltage seen at the terminals. The thing is, if the current is 0, okay, if the current is 0, then whatever is seen at the terminals will match with this third term directly. That is the reason why I use that phrase. This is also proportional to IR. So, the more you generate the field current, more you push the field current into the rotor winding, more will be the air gap flux that it will create. The more is that air gap flux that it will create, larger will be the voltage which will be induced in the 3 phases A, B and C. So, more will you see the open circuit voltages across it, that is the basic idea. And this rotor current, the rotor winding on the generator is also called as rotor current on rotor winding on the generator is also called as field winding, because it sets up a DC field, so to say, and the current that is carrying is also called as field current. In many places it is also shown as IF, and this expression here that we have, this expression here says that this open circuit voltage is proportional to the field current. So, this is the way I control my voltages, which are, see, synchronous machines are the voltage generators. They are the sources which generate voltages in the grid. Others are using those voltages, maybe adding, subtracting also, but they are not really setting this. But here is a 1 kV generator, it actually generates that whatever voltage I want to generate, and I have control on it because I can control this value. Then you connect it with a step up transformer. So, bring it maybe to 132 kV, 220 kV, 400 kV, whatever, connect it to the grid, then grid takes it around here, there, and then step it down, and then is used by the, you don't generate it at 400 kV, that we have seen in the transformers story also. So, coming back to this derivation, I will therefore write this as E t times e to the power j omega s of t, all right. So, now you have got, this is a complex number, to emphasize this I will put a bar, and this is a complex number, I have already put a bar there to indicate that. So, now because real part of this is equal to this is equal to this, what I can do is I can write this as real part of V A. Now, I am taking this to left hand side, I am taking this also to left hand side, and all of them contain e to the power j omega s of t term. So, I am going to take that as a common term, and hence I am going to write this as V A minus j excess I A minus of E of t times, beautiful, no, so much simple it has become, real part of this will become equal to 0. So, the real part of this will become equal to 0. Now, if this is true, if this equation is true all the time, this equation is true all the time, what happens? this is basically a unit length phasor rotating at a speed of omega s. So, it is always non-zero, it is always non-zero, and for all whatever value that this takes, this product into this is always 0, this product into this is always 0. So, this is only possible if this thing which is by which this amplitude is scaled, this term here itself becomes 0, then only this will be true for it to be true for all t, for this to be true for all t, even when you are just looking at the real part, even when you are just looking at the real part, because you know that, see, just if I talk of e to the power j omega t and I say real part of e to the power j omega t is equal to 0, then that is possible at this also, and this is possible at this also, pi by 2 and minus pi by 2, this real this is the e to the power j omega t operator, and its real part will become 0 exactly at 2 angles. But this is for, so it becomes but true for capital T by 2, where capital T is the time period, and minus and plus 3 T by 4 at 3 capital T by 4 at these two times, e to the power real part of e to the power j omega t will become 0. But that is not what we are saying here. We are saying here the real part of e to this whatever it is, this number times this is always 0, for all t it is 0. So, this is a grand statement, you know, it is a much bigger statement, and this is only possible if this whole term goes to 0. If it does not go to 0, then I can simplify it and find out a particular position where it will not be 0. I will leave this thing for you to do as a homework. But if you say that this is not 0, write it as a complex number, magnitude angle e to the power j phi or something like that, push it into this, then substitute that e to the power j omega s of t plus phi to 2 pi or something, and show that at that point, you know, at that point its value is actually non-zero. So, this whole thing is true for all t. If it has to go to 0, then it means that this has to be the argument, this argument has to be equal to 0. In other words, even though this is a reference phasor, it should still be shown as I of a. So, therefore, V of V A, I am sorry, this is V A. So, this is also V A minus j x s I A should be equal to E of t. This should be equal to E of t. So, I have now got the equivalent circuit. Now, I have got the equivalent circuit of the synchronous machine. So, I have this, this is my V A, and by the way, if the machine has the windings, if they have resistance also, so if the windings have resistance also, then I should put a I will write it as E A for A phase. So, E T and E A are the same. Yeah. So and if there is a resistance, then this can be because actual windings will have resistance also, you can replace it by stator resistance plus R j x, that would be called as the synchronous impedance. So, this becomes the equivalent circuit of the motor, synchronous motor. Cool, is it not? Pretty cool, I would say. The equivalent circuit is turning out to be just as simple as this. Now, if you want to draw the phasor diagram of this, this is VA. Let us say that it is carrying a unity power current, this is motor operating at this, then this will become J excess I A. Since I have to do minus J excess I A, I have to do minus J excess I A, V A minus J excess I A, and then oops. This will become my terminal voltage E of A. So, this is the way I can write the phasor diagram. I can write from this equivalent circuit, I can write the phasor diagram of the machine, and you can write it for leading power factor, lagging power factor, whatever. I just demonstrated you this. Now, what more can I do with this phasor diagram? What more can I do with this phasor diagram? I can, for example, now derive the power and torque equations. I can derive the power and torque equations in terms of ET, VA and the synchronous reaction. The synchronous reaction is also called as sometimes the impact is also inferred as armature reaction, because the rotor is carrying field flux. It is inducing voltage in the stator winding. In turn, the currents are there. In turn, those currents are, the stator is also called as armature. So, those armature currents are creating another rotating MMF field, and that rotating MMF field is interacting with the FR, which is created by the travelling wave of sinusoidally distributing travelling wave, rotating travelling wave of the rotor, and you get a net superposition of these two, which is the actual flux distribution which is happening in the air gap. And so, this is consequence of rotor plus the reaction of the armature or stator, and hence is this synchronous reactance, or the issue J excess I A is also called as the armature reaction voltage or the MMF. Now, let us to calculate power, and this is A phase equivalent circuit, right. This is A phase equivalent circuit. We can similarly write the B phase and C phase equivalent circuit, but we will not do it, because for the balanced machine, all the three, once A phase is known, everything is known electrically for B phase and C phase also. Active power and reactive power in the three phases are going to be the same. Voltages are going to be, terminal voltages are going to be all equal in magnitude, 120 degree apart. Similarly is for the current. So, there is no need to write for B phase and C phase the equivalent circuit. It can be written, but not required. The A phase power which is transferred is the total power by 3 watts, because each of the, if the machine, if the motor is rated say 3000 watts, then 1000 watts contribution is coming from A phase, 1000 watts contribution is coming from B phase, 1000 watts contribution is coming from the C phase. So, now we are trying to get a equation for expression for PA. So, what can be the PA be written as? It can be written as, what is EAIA star? It is the complex power. What is real part of EAIA star? That is nothing but the PA, and it is also same as EA star real part of, if you take, suppose EAIA star is A plus JB, you take complex conjugate of it, complex conjugate of this, that is E A star I A, that is going to be A minus J B. In either case the real part is still the A only. So, therefore, the P A can be written as real part of E A I A star or real part of E A star I A. Now, let us write the expression for I A from this our equivalent circuit. So, I A can be written as V A minus, this being a phasor voltage, V A minus E A divided by J X S. So, E A star I A is going to be E A star V A minus J, I am sorry, V A minus E A by J X S, which is E A star V A by J X S, minus 1 can be written as plus J square, and J square divided by J will cancel out and leave you with 1 J, and what is complex conjugate of any number times the number itself? The square of the magnitude of that number. So, therefore, it is E A square, this is a real number, real positive number, divided by J of divided by simply x of s. So, this number is purely imaginary number, this number is purely imaginary number, it has no real part. So, if I am for looking at power, if I am looking at the real part of this, let me not do it here, let me write it here. So, if I am looking at real part of this, it is going to be same as real part of E A star V A by J X S, because the second term does not have any real part. So, therefore, the real part is only coming from the first term. So, if E A was written as some magnitude E A at an angle of delta, then E A star will be magnitude of E A at an angle of minus of delta. Since the V A we have in this expression, we are once we have written this expression like this, it is our choice now. Now, this is always true equation. While deriving it, I took I A as reference, but I do not need to now stay all the time stuck to this that I A is reference. I can even in this equation any one quantity can be reference and the other angles will adjust appropriately with respect to that. So, therefore, I am going to take V A as a reference, and because I am taking V A as the reference. So, I am saying that the internal EMF is having an angle delta with respect to V A. So, then this term can be written as the real part of E A, only the magnitude V A by x s e to the power minus j, because of this j because E A star, E A is just the length E A into e to the power j delta, minus E A star is same length E A into minus of e to the power j delta, and this 1 by j which is sitting here, this can be written as e to the power minus of j delta by pi by 2 e to the power this is 1, this is j, this is minus of j, which is 1 by j is nothing but j multiply j numerator and denominator j by j square is minus 1. So, it is minus of j. So, therefore, this thing comes out, but to write, if you are just interested in this being a real number, and since you are only interested in this, So, it will become cos of delta plus pi by 2, which is same as EA VA by XS minus sine of delta. It is same as minus sine of delta, and this is equal to left hand side. What is it? This is the real part. This is the power associated with the A phase, but the power associated with A phase is what? Total power, the 3 phase power, the total power divided by 3. So, therefore, PT by 3 becomes equal to this, or in other words, PT becomes equal to minus of 3 EA VA by XS sine of delta, and because the synchronous machine is always rotating at the synchronous speed, its rotational speed omega m is same as omega s, 2 pole machine. So, therefore, this will become minus 3 EA VA by omega s XS sin delta. So, this unit is in watts, this unit is Newton meter. So, this becomes the, so now you see from the equivalent circuit, given the synchronous reactance of the machine, I can, if you say I am loading machine with so much Newton meters of torque, its open circuit voltage is so and so, its terminal voltage is so and so, I can immediately tell you at what is its torque angle. Let us do a couple of problems, put this to use put this to use and see how it helps in solving the problems. So, let me take one simple problem here. This is again from Professor Pai's book. I will copy, let me paste it here. Okay, a 3 phase Y connected 60 hertz synchronous machine with 2 poles has synchronous reactance of 5.0 ohms per phase. Now, synchronous reactance unit is ohms because it is reactance, right. So, therefore, its unit is ohms and it is a phase quantity. So, therefore, per phase we wrote it is used in the equivalent circuit of A phase. The machine, while operating as a motor, takes a current of 30 amperes and the voltage per phase is 254 volts at a power factor of 0.8 lagging. So, if I am taking the voltage as reference, then the 30, so cos of phi is 0.8. So, phi is 36.86 degrees and 36.86 degrees. So, therefore, this is lagging current, leading current. So, because the current is leading, so I will write it as plus 0.3686, this much amps and this much volts. So, find EAR and TE, that is the first question, and if the machine has a windage, friction and core losses of 400 watts, what is the useful shaft torque, what is the efficiency, that is the other question. So, what is our equation? VA minus JXS IA is equal to the terminal voltage EAR. Here I have used the the EAR and ET are one and the same. So now 254 angle 0 minus J phi 30 into 30 at an angle of 36.86 degrees is equal to ET and so so I will just show you answer I have already written, I will just illustrate you. This is my V terminal voltage, this is my current. Now this J this angle is 36.86, this is current. So if I this 150 5 into 30 is 150 and this is J positive J 350 150 positive J 150 further moving 90 degrees taken ahead of 36.86. So if I have this with minus sign here, then the same thing I should write minus of. So this is 150 angle here and so these two lines are basically parallel. So this is 90 plus 36.86. So this is 90, this is 36.86 and now this length is my ET, this length is going to be my ET. So it is clear that it is going to be larger than 254, it is going to be larger than 254 and in this example when you solve it, it will turn out to be 364 at an angle of, again you can see that the angle is going to be negative and minus 19.23 degrees. So the point is, interestingly one more point that you have come out, which has come out of this is interesting point, one more point interesting that has come out of this is, we had derived that PT is equal to minus 3 by minus 3 EA VA by XS sine of delta. Now because PT is greater than 0 for the motor, the power which is transferred, mechanical power which is transferred, which is drawn from the electrical side and transferred to the mechanical side, that is taken as positive, that is greater than 0. So the motor will have delta less than 0, this is what the motor will have. Okay. So this is what we also saw, that in this case our motor angle is coming out to be minus of 19.23 degrees and of course the omega m is 377. So therefore now once you have got the delta, you substitute, you know EA, you know VA, you know delta, you know XS, substitute these 3. So you will get this power transferred, the power transferred at the electromechanical level as substituting in this equation here, you will get that as 18286 watts, 18286 watts. Now if you just divide it by omega s, the synchronous speed, and this machine is a 60 hertz machine. So 120 pi comes out to be 377 radians per second. So if you divide it by 377, you would get a number which is corresponding to 48.5 Newton meter. But this 48.5 Newton meter is not available. Why? Because look at the B. So this is TE, which is actually for an ideal machine, frictionless, no other losses, so on and so forth. Whole of this TE would have been available for doing the mechanical work. So we have found this and this, but then in the part B, what is being said if the machine has windage, friction and core losses of 400 watts. So windage losses, friction losses and core losses. Why do we say core losses? Core losses because AC winding is having alternating flux. Alternating flux will create hysteresis and eddy current losses. So, you need to laminate also the stator winding because it is, and there is no problem in laminating because it is not anyway rotating. So, core losses will be there. Friction, because anything when it is rotating it will create a friction. So, friction has to be overcome. Windage is because it is rotating in air. So, higher the speed you rotate, there is some windage loss which is wind. Windage is not coming from winding, windage loss is coming from the word wind. So, like the fan when it is rotating, it needs some power because it is cutting wind, and higher the speed at which you rotate, the higher will be the power that it will consume, because it is windage losses related to wind will also grow. So, and the rotor winding, does it have a core loss? No, the rotor winding of the synchronous machine does not have a core loss. Why? Because the 3-phase rotating field created from stator currents is also rotating at synchronous speed. Rotor is also rotating at synchronous speed. So, there is no relative change of flux seen there. So, therefore, nothing will come out of that. No EMF will be induced from there in the rotor, and therefore, nothing will, no currents will flow, nothing is going to happen. Rotor winding is carrying a DC current and it is sitting on the rotor and rotating rotating along with the rotor. So, it will also not create any, the flux is not changing with time, it will not also see any change in flux with time anywhere. So, therefore, you will not have any eddy current loss or hysteresis loss associated with the core. So, the core need not be laminated also to do that, to take care of that. And when if the core is solid, you are lucky, right, because when something is rotating at 3600 rpm at 60 hertz or 3000 rpm at 50 hertz, if something is rotating at that speed value and if it is laminated and stuck together, it is much more easy for it to fly apart, right, due to centrifugal force or centripetal force, but that problem is not there in the rotor. Only the stator has to be laminated. The core losses are happening in the stator which is non-rotating. So, what happens then that out of this 18286, 400 watts is gone, 400 watts is gone. So, you have 17886 watts only available for doing useful work, and the machine is rotating. So, if the what is the useful shaft torque, what is the efficiency? So, if this is only available for doing useful work, divide this by 377, the synchronous speed of the machine, and you get a number which is 47.44 Newton meter, which is only available for doing what is the useful shaft torque. This is only available for doing actual mechanical work outside, which is the useful shaft torque. And what is the efficiency? Efficiency is 17886 divided by 18286 into 100, and this efficiency should be some 97. I have not written it down here, you calculate it, but I think it should come around some 97% or so. So, this is the efficiency of your rotating synchronous machine. Now, before I close this lecture, let me just mention a small point here, that when dealing with the synchronous generator, usually what we do is, so we had this as the equation for for the synchronous motor. So, if the if this is a winding and the current is flowing, this is the A phase winding of the armature and the current is flowing, this is the terminal VA and something here that is generated is ET, this is our notation. Then for the generator we will follow this as our convention. The generator is generating voltage which causes a current to flow out, like we had the primary winding and the secondary winding like that. So, therefore, the IA for when dealing with generator, the IA should be replaced by minus IA to meet this generator convention, and so this equation becomes VA plus J XS IA equal to EA. In other words, this is my EA, this is my, the generator delivers a current of IA, this is the synchronous reactance and this is the voltage which is seen at the terminals. Advantage of doing this, which probably I will take up in the next class, is that for generator the torque angle will turn out to be positive and for motor the torque angle turns out to be negative. So, that looks to be very neat and clean and elegant. I will just have that synchronous machine diagram somewhere I have here. Yeah, so the both these diagrams you can see here. Here the current is going into the machine, this is my machine, current is going into the machine. Here this is my machine and the current equivalent circuit of the machine, the current is coming out of the machine. So, therefore, the two equivalent circuits, this equivalent circuit can be written as, in other words, the two written as VA plus J XS IA. When dealing with generators, we use this as my equation. When dealing with motors, we use this as the equation, and usually we deal with motors separately and generators separately, simultaneously they are not there. So, do not have to worry about it. We will take a break here. Thank you. We will continue in the next class.